Hello. In this video, we are going to see some example, or one example of a function. It's the one that helps you calculating the orbital period. I think it's one important function, and I was going to give you some examples, and I think this is an important example. What is the objectives of this video? It's to understand the function used to calculate the orbital period as an example of a function. We will review where this function comes from, and this is coming from Kepler's third law, and we will see the relation between satellite orbit and orbital period. Okay, what we need to understand this video? Okay, it's not very much. The idea is that some knowledge about physics and astronomy, astronomy is not necessary, physics a little bit, because we are going to see this orbital period from a mathematical point, okay? And some ideas of algebra and geometry, and I think it's more than enough to understand everything. Okay, let's start with reviewing one idea. The idea is the major semi-axis of an ellipse. As you can see in the plot, we have an ellipse plot in blue, and the semi-axis is the distance between the center of the ellipse and this point. Okay, this is going to be the major semi-axis. It's a distance. A is going to be a real value, positive real value. In this case, when we are working with ellipses, A, the major semi-axis, is positive. Okay. So why is this definition here? Because I want you to have the picture in your mind. When I'm going to talk about the major semi-axis, it's exactly this distance you can see in this slide, okay? This distance. Okay, perfect. Orbital period. Orbital period definition is the time it takes for an object to complete a full orbit around another object. For example, if we have a satellite orbiting the Earth, the orbital period is the time it takes to the satellite to complete a full orbit, to pass through 2 times at the same point. Okay? We can define the orbital period of a satellite. We can define the orbital period of a planet, for example. Okay, it doesn't matter. How do we calculate the orbital period of a satellite orbiting the Earth, for example? Okay, it's very easy. The idea is to use Kepler's third law of planetary motion. This law states that the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of the orbit. Okay, so this law, that is one of the most important laws in physics, is states or relates the major semi-axis with the time it takes a satellite to complete a full orbit. Okay, and we will work with this function. Okay, my point in here is not to prove or to demonstrate this law, but to use this law as a function, as an example of a function. I think it's a very interesting function. Okay, translating third law of Kepler into formulas, we have this one. The orbital period that we are going to call T, or P, depends on the book, it's defined as 2 times pi square root of a cube, where a is the major semi-axis, divided by gm. What is gm? G is the gravitational constant and m is the mass of the Earth. Okay, be careful. I'm being a little bit risky here because I just used the mass of the Earth. Be careful, because m could be the mass of the main body from which we are orbiting around this object. Be careful with that, okay? Could be Earth, could be the Sun, could be Mars, could be Jupiter, I don't know, okay? So be careful with that. Should be m is the mass of the main body we are orbiting, okay? Normally, we don't write gm all the time, g times m. We denoted this like mu. Mu is the standard gravitational parameter, and it's going to be denoted like the Greek letter mu. Okay, so the formula we are going to use is this one: 2 pi square root of a cube divided by mu, where mu is the standard gravitational parameter. Please remember that. Okay, so it's a very simple function. It's a very simple function. T, it's the function that depends on the major semi-axis A. So depending on the value we put on A, we will have a different orbital period. Okay, guys, let's see an example. Before the example, it's a function. If we are looking this example from a mathematical point of view, my interest now is to know a little bit more about this orbital period. Is this function increasing? Is this function decreasing? I don't know. So let's study this function a little bit, and then we will see some examples. Okay, first, if we want to know if this function is increasing or decreasing, we are going to use the first derivative of the function. Please, let's highlight, or let's see that I just wrote t as a function of a, and this is where the mathematical part comes from. Okay, and I'm just here rewriting the function in a different form to make it easier to calculate its derivative. It's not necessary, guys. Probably you know perfectly how to calculate the derivative, and you can do it faster. But since I don't know how much you know, I prefer just to write this in a simpler way. As you can see, I just divide I have a quotient and a square root of the quotient, and I just wrote the square root of the numerator and the square root of the denominator. Where have you done this? Here, because the exponent, I just wrote the exponent divided by 2. That means the square root. Okay, the square root of mu, it's just a constant. So I just put all the constants together here. So this function is just a number times a power 3/2. Okay, so it's a function, it's a power function. Okay, so what is the derivative of this? Remember that the derivative, if we have a constant multiplying the function, the constant remains. So 2 pi over the square root of mu is here. Then how do we calculate the derivative of a power 3/2? The exponent goes down. As you can see here, we have the 3/2, and we subtract 1 to the exponent we had before. So it's 3/2 minus 1, that is 1/2. So the derivative is very easy. So what do we know about the derivative? Remember something that we mentioned at the beginning. Definition of the major semi-axis is always positive. So when we put here something positive, the square root is positive and this number is positive. So the derivative is going to be positive all the time. Okay? So let's see. Critical points. Critical points is where the derivative equals to 0 or the derivative does not exist. In this case, this derivative is equal to 0 in a equal to 0. This makes sense when we are calculating orbital periods. If the semi-major axis is 0, we don't have an ellipse, we just have a point. Okay, there is nothing, it's just 1 point. So, can we evaluate the function at 0 from a mathematical point of view? Yes, but in a real world, it doesn't make sense. Okay, so that is the reason I just eliminate 0 from the domain. But strictly as a mathematical function, makes sense. You can just replace a by 0, and the period is 0. Okay, it's not orbiting. Second, there are no critical points within the domain because the only one is 0, and 0 is we are not going to consider 0 from a physical point. Because the derivative is positive. When we replace a by a positive number, square root, as I told you, is a positive, then it's always positive. What does this mean? That the function is increasing all the time. If the derivative is always positive, that means that the function is increasing. So what is the plot of the orbital period? Here you have the plot. Depending on the x-axis, we have the major semi-axis. On the y-axis, we have the time in hours. Okay. Normally, depending on the units you use for the gravitational parameter and the units you take for the major semi-axis, normally the period is given in seconds. I just divided by 360 to obtain hours. So the plot is more or less the same if you plot it in seconds. But we are more used to hours, so just is here the plot. And as you can see, the longer or the longer the major axis is, the more time it takes to complete a full orbit. Okay? So it's an increasing function. The farther we are from the center, or from the Earth in this case, the more time we need to complete a full orbit. Okay? That is interesting. And it's an idea that we must keep in mind. Okay? always remember, orbital period increases with the major semi-axis. Just to finish, just a brief idea. Normally we have several satellites orbiting around the Earth, and we divide these satellites in three types. LEO, that means low Earth orbits, that are very close to the Earth. It's just about 400 kilometers till 2,000 kilometers is low Earth orbit. Then you have medium Earth orbits, MEO. It's all this range in which you can find here, more or less here, the GPS satellites, and high Earth orbits, very far from the Earth, like geosynchronous orbits that are around here. I think the distance is more or less 40,000 kilometers from the Earth. Okay, so this is just a way to separate or to classify the satellites orbiting around the Earth. Okay, guys. So what have we seen today? We just study an example that calculates the orbital period and how this orbital period is related with the major semi-axis of the orbit. I hope this is helpful for you. Thank you for your attention and see you in the next video.